I was trying to figure out where those numbers came from, and it didn't make any sense. And then I realized that the book really wanted to say 223.4 grams of ferrocene and not 23.4 grams of ferrocene. So that made more sense. And I looked back at all the other editions in their notes, and they have it wrong in all of their notes, so I don't know what they're doing. So I just wanted to bring this up. And if you actually calculate the moles, you'll see that that 223.4 is actually going to be 4 moles of ferrocene. So that's all it's representing. But of course, the total mass of our reactants would equal to our total mass of products. And if you convert those to moles ferrocene and moles O2, and then use your stoichiometry to figure out moles of Fe2O3, you can then would find that would produce 319.4 grams. So it's all related. So I just wanted to show that. I don't know what the book had, but it's now fixed in my notes. So we started talking about theoretical yield. And we know that the theoretical yield comes from our limiting reactant, because once that's gone, we can't have any more reaction. So if our reactants are exactly set up perfect, we might not have a limiting yield. For example, if we figured out with these two, we'd find that both of these, we started with this one, we predict 319.4 grams of our product. If we started with this number, we'd also predict 319.4 grams of our product. So you can go ahead and try that. So that one's set up perfect where neither is limiting. But most reactants will have a limiting region. You won't always have it set up perfectly. So our limiting reactant is going to tell us our theoretical yield. We cannot make more than what we have the least of. And not by mass, but the least of what we're going to produce. So to actually produce our percent yield, we have to know what we actually make. And I have to tell you that you cannot predict what you're actually going to make. There's a lot of things that could happen in the lab. If you're a very, very, very good chemist and you know what you're doing, you might get a pretty high yield if the reaction allows it. In organic chemistry, not all reactions allow for 100% yield based on things like stability. But assuming the reaction will go to completion, there's things you in the lab might do to make it not go into completion. Maybe you measured something wrong. Maybe you lost some of your product, so you have a lower yield. So your actual yield is your actual measurement when you do the reaction in the lab and you find a number from it, whatever your product is. And then to figure out your percent yield, it's just your theoretical yield. And your actual yield divided by your theoretical times 100. And of course, you cannot make more than your theoretical yield unless if you did something wrong. So you should not have a yield greater than 100. So unless if you added more of the reagents in than you calculated, or if you, let's say, didn't remove solvent, we'll be talking about solutions in the next reaction, in the next couple of slides. That could affect your yield. But theoretically, your yield should never be over 100 unless if you did something wrong. Alright, it's not going up. I'm not going to fight with it. So let's look at an example. because that's the best way to look at these. So in this example, we have 28.6 kilograms of carbon elemental allowed to react with 88.2 kilograms of titanium oxide. In the reaction below, and then we find that we actually obtain 42.8 kilograms of titanium. Find our limiting reactant, theoretical yield, and percent yield. So we're finding a bunch of things. And in this case, we do have to do that. We can't really find our percent yield until we find our limiting reactant and our theoretical yield anyway. So these are just specifically asking for those. But if I ask for the percent yield, you'd have to go through the same steps, because you can't figure out your theoretical yield without knowing which is limiting. And it's not typically very easy just to look at a reaction and determining which is limiting. You have to actually do the calculation. So we're going to go through this example. So first off, we're told that we're reacting, well, one, we're given our equation, and our chemical equation is balanced. You always want to double check that. So we're given that we have 28.6 kilograms of carbon and 88.2 kilograms of TiO2. That's great. We're told what we have. We can calculate, using these two numbers, our limiting reagent and our theoretical yield. Now there's another number that we're given, and we're given the amount of product obtained. That's our actual yield. That's what we obtained after we did the reaction. Put that number on the side. We don't need it until we figure out our percent yield, because that doesn't tell us anything right now. All that tells us is the actual yield that was formed. So let's start with these two. So the first off, we're given grams, but to do our conversion, we need to convert that to moles. So there's a couple of things that we need to do. First, we need to convert our kilograms to grams, because our molar mass on our periodic table is in grams per mole. So we need to relate that. So we need to convert that to grams. Once we have our mass in grams, then we can use our relationship from our periodic table molar mass to convert to moles. For carbon solid, that's just going to be 12.01 grams per mole, because carbon's in its elemental form. But for TiO2, we have to calculate its molar mass, and you should be able to do that at this point. Looking at the periodic table, we calculate it to be 79.87 grams per mole. I'm not going to always be calculating the molar mass over and over again. At this point, you should be able to do it. And again, I recommend working these problems with just the periodic table in your calculator and not looking at this until the end. You get stuck and look back, but if you can do these all on your own, you should be fine on a test or quiz. So once we have our moles of our two starting material, we're going to use both of these to predict how much moles of our product we expect. And we're going to use our stoichiometric relationship from our reaction. So for carbon, we see that we have 2 moles of carbon is going to form 1 mole of, and our actual yield is titanium, so that's what we're going to use. We weren't given the actual yield of CO, so we don't really need to look at that one. So we have 2 moles of carbon equals to 1 mole of titanium. And then we have 1 mole of TiO2 equals 1 mole of titanium. So that's just our coefficients. So we'll use that conversion to figure out our moles of titanium. Once we have those 2 numbers, whichever of those 2 numbers is the smallest amount, that's going to be our theoretical yield. And our limiting reagent is the starting material that gives us our smallest moles of our product. And then once we have our theoretical yield, then we can figure out our percent yield. And in this case, our actual yield is given to us in grams, so we can either convert our theoretical yield to grams, or conversely, we can convert our actual yield to moles. But to do our percent yield, they have to be in the same units. So I'm going to do converting this to grams, but you'll get the same answer if you convert your actual yield to moles and use your moles titanium. You just have to have them in the same unit, because it is part of a whole, but they have to be in the same measurement. So it's given to us in kilograms, we'll do that. We have to convert one or the other. Then our percent yield is just our actual yield, that's what we were given in kilograms, divided by our theoretical yield, which we converted to kilograms, times, of course, 100 because it's a percent. Don't forget to multiply by 100. So let's actually go through these calculations. So first we need our relationships. And we know 1,000 grams equals 1 kilogram. I saw this on the exam a couple of times. It's not 1 gram equals 1,000 kilograms. Remember, kilograms are bigger. So 1,000 grams equals to 1 kilogram. We can calculate our molar mass of TiO2. That's it. Make sure you can do that on your own. Our molar mass of titanium is just from the periodic table because that's in its elemental form. So we can figure that out. Our molar mass of carbon, again, is in its elemental form, so that's just our atomic mass in the periodic table. And remember, this is all in grams per mole. And then we just talked about our relationship. 1 mole of TiO2 forms 1 mole of titanium. That's from our equation. When it's balanced, 2 moles of carbon equals 1 mole of titanium. I'm really breaking this down so you guys can follow me. So let's actually apply this. So what we're going to do is convert to our moles of our product. Where's my pen? There it is. So we are starting with carbon. And we want to convert that to our grams. So our kilograms cancel out. Now we want to convert that to moles, because our relationship of our equation is in moles, because remember, each molecule and each atom has a different mass. So we want to convert that to moles. It's comparable. Our mole carbon go on the top, and our 12.01 grams of carbon goes on the bottom, so we can cancel out. So if we calculated this, we'd have our moles of carbon. You don't necessarily need to get that number. So now we want to relate this to our moles of our product. So again, we're using our periodic table. Our 2 moles of carbon equals to 1 mole of titanium. So our 2 mole carbon is going to be at the bottom, so it cancels out. That's why I'm keeping that C. And 1 mole of titanium at the top. So this will give me this in moles. I could convert this all the way to kilograms now, but then I'd have to do that for both of the examples, and I won't need to do that for both. So you can stop at moles just for your comparison, but it's up to you. I'm just going to not round too fast so I don't have problems with my significant figures. I know I should have 3. We're going to do the same thing for our other starting material. And here's another thing, always double check. Make sure you're using the right numbers. So the problem told us we started with 88.2 kilograms of titanium oxide. Don't switch that to carbon. Or make sure you're writing the numbers down correctly. So those are just small calculation issues you can have just by trying to work quickly. So always double check you're writing down the right numbers, so you don't make a simple mistake. So first we want to, of course, calculate this, convert it to our grams, because our molar mass is a relationship between grams per mole. So our kilograms cancel out. Now we want to convert that to moles, and we're going to use our molar mass that we calculated earlier. No one turned anything in. Okay. So once we have this to moles of titanium oxide, now we can relate this to our product. Now this is a 1-to-1 mole ratio. It won't change the number, but I want you to always include this step because it was really important in the example before. So if you always get in the habit of including it, you won't forget to do it. And this step is really important because that is actually relating our moles of our reactant to our moles of product. So when we figure that out, now we have these 2 moles of product. So the question is, which of these 2 is limiting? So our TiO2 gives us a smaller amount of moles, so that's going to be our limiting reagent. Once we run out of TiO2, we can't do any more reaction. So even though we have less mass of carbon, that's not a good indication. We have to do this full calculation so we can fully understand what's happening. Because of course carbon weighs a different amount, and our relationship with our reactants and our products. So our limiting is going to be TiO2. So this is the moles we're going to calculate for our theoretical yield. It's very common that students want to say carbon's limiting, the one that gives you the most moles. But remember, once you run out, you cannot form any more product. That's why our limiting and our actual yield is coming from the one that will predict the least amount of product. We want more product, then we need more carbon. So now that we have that, now we can calculate our percent yield. Again, our actual yield is in kilograms, so either my actual yield needs to be in moles or my theoretical yield needs to be in kilograms, because they have to be in the same units. So I'm just going to convert my theoretical yield to kilograms. But if you kept your theoretical yield in moles and converted your actual yield to moles and did the percent yield, you'd get the same number. So you can always double check that. Neither is more wrong than the other. But what would be wrong is for me to take my 42.8 kilograms titanium and divide it by my moles of titanium, because they're not in the same unit. So they have to be in the same unit, whether it's grams, kilograms, moles, milliliters, they all have to be in the same unit. So something has to be converted. I'm just going to convert the theoretical yield. But again, you can try it the other way and see what you get. Oops, forgot my 3. And again, because I am not done with my calculations, I don't want to round just yet. So I'm just going to keep those. Remember, I only have 3 significant figures. So I'm just going to convert this to my mass using my molar mass of titanium. But again, this is in kilograms, so I'm going to convert this to the same units. So I will convert it to kilograms. So what we see is our theoretical yield is 52.9 kilograms. That makes sense. We should have a higher theoretical yield than our actual yield. So now we can calculate our percent yield. That's just going to be our actual yield, which was given. And it has to be given. You cannot calculate an actual yield. Divided by the theoretical yield in the same units. Kilograms titanium cancel out, so that's fine. And of course times 100, because this is a percent. So what we find is our yield is 80.9%. And you cannot figure out your percent yield if you don't know your theoretical yield. So you do have to go through this. For the iClicker example, here's the iClicker example. In this case, we already know what's our limiting reactant. What's our limiting reactant? Without doing any calculations, what's our limiting reactant? Our limiting reaction is La2O. How do I know that? It tells me water is in excess. By being in excess, that means it's going to be left over after the reaction's done. I don't need to know how much water I'm using. I know I'm using more than I need. So this tells me that water is in excess. I don't need to do anything else as far as predicting which one is my limiting. It has to be the other one because the equation tells me water is going to be left over at the end because it's in excess. So that's easy there. But I do need to know my theoretical yield. So I will have to do a calculation using the mass of my starting material, which we know my limiting reagent is Li2O. We were told that because the other reagent is in excess. And we have our actual yield. Forget about your actual yield now. We don't need that till the end. So the first thing we need to do is calculate our theoretical yield. So for this one, again, we need to know our molar mass of our Li2O. Now in question 4 in your quiz, I gave you your molar mass of H2O and CO2. Though I know you can calculate it, I was just trying to save you time. If I give you a molar mass, don't waste your time by trying to calculate it. I'm not trying to trick you by giving you a wrong molar mass. So Li2O, if we figure out our molar mass, it's 29.88 grams per mole. Again, make sure you can calculate that. If you're having trouble with molar mass, please come see me. And our molar mass of our product is 23.95 grams per mole. So that's your first step. You have to calculate those. So let's start our reaction. So we know we have 25.0 grams of our starting material. We don't need to know our molar mass of H2O. It doesn't matter because it's in excess. So we won't be predicting how much product we could form with it. So we have to convert this to moles so we can figure out how much of our product we expect from 25 grams of Li2O. So with lithium oxide, what we're going to see is our molar mass is our conversion. So we want our grams on the bottom. And our mole at the top. So this will give us our moles of our starting material. Now that we have our moles of our starting material, we can relate our stoichiometry of our reaction. So we have 1 mole of Li2O for every 2 moles of our lithium hydroxide. And I know that based on my stoichiometry of my balanced equation. So I want my moles of lithium oxide on the bottom. So that cancels out. And that equals my 2 moles of LiOH. Again, moles LiOH won't cancel out Li2O. So we have to put the correct moles at the bottom. So now we know our moles of LiOH. And you can figure out what that is, but we don't really need to know what those moles are because our actual yield is given to us in grams. So we might as well just go ahead and convert this to grams. We don't need to compare how much moles water is formed because we already know it's in excess. We already know we'll have more moles of water. Plus, we don't even know exactly how much we started with, and we don't need to. So to convert this to grams, we can use our molar mass of lithium hydroxide. We want our 1 mole of LiOH at the bottom and 23.95 grams of LiOH at the top. So this will give us our theoretical yield of lithium hydroxide in grams. So we should only have 3 significant figures. So I'm just underlining those. So this is our theoretical yield. We are given our actual yield in the problem. And at this time it says actual yield. So to figure out our percent yield, it's just our actual divided by our theoretical times 100. So plugging that in, 22.3 grams of LiOH is what we did retrieve, but we should have made this much, 40.1. So our percent is 55.6. And of course, for the iClicker questions, that is B. So before you go today, I have another 5 minutes with you, and I want to start you getting started with solutions. Now, I don't know why all this other stuff wasn't in chapter 3, and this isn't a separate chapter, but it's all related. So here's the thing. A chemist doesn't do very many reactions in the solid state. The solid state means your compound as a solid. Compounds in the solid state don't typically react that well. There's not much molecular movement, and they're really attracted to other compounds in the solid state, which is why we form solids. So most times, you use solvent to dissolve your compounds to get it in the liquid state. Now there are solid state reactions, those are called solid state reactions, but again, not that many compounds can really undergo a solid state reaction because we don't have that much molecular movement. So we'll typically dissolve our compounds. So that brings us to solutions. Now in this class, we're mostly going to be working with salt solutions, meaning ionic compounds dissolved in water. But when you get to organic chemistry, we use organic compounds, and we're not really using water as a solvent too much because most organic compounds don't dissolve well in water. But for this discussion, we're going to be thinking about water as our solute, but we can use the same concepts in any type of situation, no matter what our solvent is. So when we take table salt, we mix it in water. It seems to disappear, but it's not disappearing. It's just getting into the liquid state to become a homogeneous mixture with water. What happens is the water molecule is represented as the red ball and the two white balls, our H and our two O's, is going to be attracted to our positive charges and our negative charges of sodium and chloride. And what it does is it surrounds the positive charges and the negative charges. And notice it's kind of different. The red balls are closer to the positive charges. The white balls are closer to negative charges. We'll get into polarity in chapter 7 and 8 and 9 in more detail. So we'll talk about that more and the physical properties that cause this to happen. But basically, the water starts surrounding individual ions and starts pulling them apart. So it's still salt, but it's no longer attracted to our sodium and chloride, but they're being pulled apart. So what happens is it doesn't look like salt anymore. Instead, it is dissolved in water. This is what we call a solution. A homogeneous mixture is a solution. We have some sort of thing dissolved in something else. So typically, the component of our solution that changes state, that goes from solid to liquid, we call that our solute. In this case, it's sodium chloride. And then the thing that's staying in the same state, in this case it's water, is our solvent. In most cases, we have a lot more solvent, and that's our major component. And that's typically what we see. Now you can get a saturated solution. You can put so much salt in a cup of water where it won't dissolve anymore. What happened there? Well, all of our water molecules are surrounding individual ions, and there's no more water molecules to dissolve the salt you have left. So that can happen, and that's called a saturated solution when your salt's no longer dissolved. This is not a chemical reaction. If we boil the water off, what are we going to be left with? Salt as a solid. We're not changing the chemical makeup of salt. We're just dissolving it. So we're going to really be getting into these equations today, but let's finish on describing solutions for the last minute of class. So they're mixtures, but their composition can vary. I can have salt water in this one cup, I can have salt water in this cup, and they don't necessarily have the same amount of salt. Depends on how much salt I put in each cup. I have sodium chloride in each cup, but that changes. The amount of salt in salt water can change the density, which is why Seawater is a different density than fresh water because they have a different amount of dissolved ions in them. So they're no longer the same, even though we have a solution of salt water. So we need a better way to describe it. Pure substances, remember, have the same composition throughout, but that's not true of solutions. So what we're actually going to do to describe solutions, and we're going to talk about that on Friday, is describe solutions numerically with how much of our solute is dissolved in our salt. So that's what we're going to be looking at. So you guys have a great day. I will see you on Friday. Don't expect these questions by Friday. It's going to take me a while to grade them.
What about Friday?
You're not going to get it by Friday. You can want it all you want. It's not going to happen.
All right.